Hello again, this is Ken Kodelik with Primus Wind Power. This webinar is a webinar regarding the air wind turbine, and you can see here on my screen the contact information for myself um, and my cell phone number here is the best way to get a hold of me, as well as my email. So feel free to do so during the webinar or when you can. So we are a division of Primus Aerospace based out of Denver, Colorado. We took over from Southwest Wind Power, who owned the turbine for 25 years. We took over in January of 2013. Southwest Wind Power unfortunately went out of business, sold all of their lines of turbines, and is no longer in existence. But Primus was established in 1989, again in Denver, Colorado, and our parent company is a precision metal manufacturing company working with Department of Defense, Aerospace, NASA, Boeing, some of the larger aerospace companies, and so on. So our business is a business within that big parent company. We want to build a turbine that has a high degree of reliability. That's very important to us because we know we're competing with solar, which is quite reliable. It also has to have great value because, again, solar is so inexpensive these days, and we're always working on innovating and doing new things with our turbine. And speaking of innovation, this is one of the innovations. This is the blue blade set, carbon fiber hand laid, very beautiful blade set with quite a few aerodynamic features that make it very quiet. It is primarily used in the cruising sailboat market, and it is a great turbine for that market because that's where sound in a turbine is of critical importance to be a very low sound machine. And almost in every case, 99% of our situations when we're installing a wind turbine, we install them with solar in this hybrid configuration you can see in this picture. Our turbines, any Air X turbine, Air 30, any of our turbines, Air 40, Air Breeze, they can all be upgraded with this blue blade set to make the turbine quieter. If you have a Breeze or a 40, you have to change out the hub because it is the Air 30 hub. You can see it's the hub that has the two blade bolt holes. Here you can see. And remember, we have some specific instructions when installing these blue blades onto a hub, or for that matter, the black blades. This particular blade set and hub, you have to measure tip-to-tip distance from the tip to the tip of each blade set, making sure that they're within a certain range, and we have information in our manual and so on that. But that's very important so you don't have an off-balance blade set on the hub. So keep that in mind. Here is the turbine itself. So we've evolved quite a bit over the years with Southwest Wind Power and us, and a lot of the turbine has stayed the same from back in 1980s, 1989 when it all started. But what has changed primarily is this circuit card right here. And specifically the control algorithm and pieces of the circuit card we've updated. Actually made quite a few changes too, especially the algorithm over the last 4 years, just to make it more reliable and robust. But the basic turbine has stayed the same, the up tower design. So this turbine is called a upwind horizontal axis turbine, starting with the nose cone, three-bladed turbine on the hub here. You got your shielded bearings and your internal bearings here, your snap ring, two sets of bearings in the face, right, through here. And then you have your stator isolator pad. Your stator itself would actually produces wild AC, unregulated AC, which then goes through the circuit card and is rectified to 12, 24, 48 volt DC. Here's your rotor, which has the surrounding neodymium magnets, right? The rare earth magnets that is what inside the stator produces that wild AC. Then you have your potentiometer harness here, along with your LED harness, your O-ring, which seals the face to the nacelle, the body of the turbine, On the side of the turbine here, you have the potentiometer screw, the pot screw, that can be adjusted. We'll talk about that a little bit. And on the belly of the turbine are the LED lights, and we'll talk about that. Here's your yaw assembly, your yaw bearing, snap rings, and slip rings brushes in your yaw assembly, which allows the turbine to spin or yaw 360 degrees on the tower so it can stay on the wind, as we say. And then down tower comes your DC power. So all power comes down tower DC with DC wiring. So keep that in mind. There are some great videos on our website. I actually just updated a couple more the other day on troubleshooting, basic maintenance, blade install, circuit replacement, and these are really important to go check out at some point if you're a dealer distributor or if you own a turbine and are working on it yourself. It's really important that you check out these videos so you know how your turbine works and what kind of maintenance that you need to do on the turbine, because there is basic maintenance that you need to perform every 12 to 18 months, and there's a video on that. Here are the turbines themselves. All of our turbines, every variety of our turbine has a 1.2 meter rotor diameter. But the visual difference between the turbines is usually the blade set and or the casting itself. So here's your land castings. All of our land version turbines have this gray cast aluminum casting or housing. And then here is your marine grade aircraft quality painted white finish. So these are what the turbines actually look like. When you get the turbine, you get the arrival kit, which includes the 3 blades, this yaw pad, which is actually inserted right here into the yaw. I make a recommendation when you're installing an air turbine, it's important that you slide the yaw, that's again this part right here, down onto the tower, push it all the way down onto that 1.5 Schedule 40 pipe, 1.9 OD, and then slightly pull up about 1/8 of an inch on that turbine to isolate the tower onto the yaw pad itself. Remember, this yaw pad is inside of here. It slips inside of here, and so that way you don't have as much down tower vibration translated through the tower itself if it's cranked down with the yaw bolts onto the yaw pad. So just a little reminder of installation there. Here again is that pot screw, and then here is your LED light on the belly of the turbine. I want to point out that that LED light has functionality, and it is a good indicator of what's going on with your turbine. If you ever call tech support, the first question tech support generally would ask is, what is the LED activity? And often in tech support, the customer will say, well, I don't know. So make sure if you're paying attention to that LED light on your turbine. So let me tell you the functionality of the LED light, and all of this is in the manual, which you can review. You get it with every turbine, and it's on our website for free under the support tab under manuals and downloads. If the LED light is not illuminated, that means the turbine is not sending power. The RPMs of the turbine have not spun up to above 400 RPMs, and therefore nothing is happening as of yet. The blade set could be spinning, but because it isn't spinning fast enough, it's not going to be sending power. As soon as it lights up solid, then that means the turbine is sending amps down the DC wire, right? And you're getting amps into the battery bank. It could be as little as, a quarter of amp, or as much as, depending on the turbine, 20 amps, depending on the wind speed. But as long as that LED light is solid, it's sending amps. When it starts blinking slowly, that means it is in regulation, which means the turbine has seen the regulation voltage set point on the battery, and it says shut down. Stop sending amps down the line, down the wire. So that's slowly blinking. If it's a fast blink, a very fast blink, that means that the turbine is in overspeed protection. Overspeed protection is somewhere between 29 and 35 miles per hour of wind. And that depends on gusts and all kinds of things going on with the wind that the control algorithm is looking at in the turbine. And as soon as that wind becomes too high, it'll go into overspeed and say shut down, apply full brake. It's an dynamic brake, and it will apply that brake, and it'll turn back on every 2 to 5 minutes depending on the turbine, and test the wind, and if it's it'll start to push amps, and if the wind is too high, then it'll shut down again. So that's the idea of that LED light. One last thing I want to tell you is something that you really need to pay attention to is when you initially plug the turbine in to the battery, when you attach the wires, you should get 2 initial blinks, slow blinks, and that is your indication that the wiring is correct, the voltage on between your turbine and your battery bank is correct, and all is well. Remember, the turbine is matched to your battery bank voltage. So if you have a 12-volt battery bank, you have to purchase a 12-volt turbine. It is voltage specific. Keep that in mind. Assembling the blades, very simple. Assemble the blade root to the hub here as shown. Then the blade, this whole blade assembly, hub and blades, then get slid onto the shaft. Then you have this jam nut here and this big Allen key that then gets torqued down onto the shaft, and then you snap your nose cone on all 3 quadrants of the hub, and that is a very simple assembly. All of our systems pretty much that we sell these days are hybrid systems. In other words, we combine solar and wind or some other charging source together. Sometimes you see solar microhydro, but more often than not, it's a solar and wind system, and that is kind of the direction that the off-grid renewable energy industry is moving towards, and it has been for a couple years, is hybrid systems. Our turbine works very well with solar. The only thing you got to keep in mind is that our turbine is a bulk charger, always looking at battery voltage. So, for instance, if you have a 12-volt system, as soon as that battery hits 14.1 volts, it's going to go to shut down our turbine. So if you have a bright sunny day and you're pushing amps into the battery bank via your solar, but it's blowing, 10 or 15 miles per hour of wind, then normally what will happen is the turbine will likely just shut down if there are no loads on the system, because as the solar panels push amperage into the battery bank, the voltage will rise, and that will then, if it rises above 14.1, it'll shut down the turbine. So that's something to keep in mind. A lot of folks get confused, or when they see the turbine not working, they then immediately assume it's broken, something's wrong with it. But it's designed to do that. As soon as a load kicks on, or clouds come over, or it's nighttime, or anything like that, then the turbine will kick back on as soon as that battery voltage drops. So that's the idea of a hybrid system. Here's your standard line diagram for a hybrid system. You have your PV through your charge controller, and you can see here the turbine does not connect into the charge controller. Another common misconception. The wires do not lead to the charge controller. Okay, so your PV, you have your ammeter, your battery disconnect, your fuse, your breaker, and so on into your batteries. We do recommend a minimum of a 400 amp hour battery bank. That's for a 12-volt system. 400 amp hours is a minimum size for a battery bank. There are some things you can do if you have a smaller battery, but if you have a very small battery bank, likely your turbine's going to have some issues, because it's trying to fill a small battery bank, and it'll be turning on and shutting down rapidly, especially if it's a high wind speed. So keep that in mind. So here's your turbine itself, and you're going through your stop switch is highly recommended. Fuse your breaker or your fuse, and your battery disconnect, and then to your batteries. So if you're interested in a diversion load controller and utilizing a resistive load such as a water heater or a air heater to utilize with your turbine, you can do that. You just need a diversion capable charge controller like a TriStar 45 or a Xantrex C40. Those are all diversion. There's also Blue Sky makes one. I forgot the model for Blue Sky, but many charge control companies now make a diversion capable charge controller. They're not cheap. They're not that expensive. They're PWM, so they're not that expensive, but it does add cost to your system. But what you can do is if you have a diversion capable charge controller connected up to your water heater or some resistive load air heater, you could then take that pot screw on the side of the wind turbine and turn that up, right? So your turbine does not shut down when it reaches battery voltage. And then the diversion capable charge controller will then just divert energy to your water heater or your resistive load, so that your solar panels and your wind turbine do not turn off when the battery bank is full, right? So that's about, I don't know, 5% of our customers install that kind of a system. Keep in mind the setup is still the same for the wind turbine. You're going directly into the battery bank, but your resistive load charge controller is coming off of there with your resistive load, as you can see in this wiring diagram, right? So the wind turbine still goes directly into the battery bank, okay? So keep that in mind. Stop switch are highly recommended. We provide a stop switch with every marine grade turbine because sailors like to have the ability to shut their turbine down in high wind speeds when they're leaving their boat, etc. Maintenance, lots of good reasons to have a stop switch. The same reasons apply for a land unit. So if you have a land unit, you don't automatically get a stop switch. So if you want to add that to your system, it's a fairly inexpensive part, about $30, and you can add that stop switch into your system. I also recommend an ammeter and some type of breaker. This is a pop-out breaker that we sell, but I typically recommend a DIN rail breaker. Works really well, but you do have to protect your wiring with your fuse or your breaker, so keep that in mind. Highly recommended. And I'll show you an example of something else we sell here in a moment. So we talked about the potentiometer earlier. Here's your voltage set points, your factory set points for voltage on the pot screw, but it is settable within this range. And this comes directly from the manual. So just to turn the pot screw up to the right increases the voltage, and to the left decreases the voltage, or excuse me, right is clockwise and left is counterclockwise. So you can change that, but remember, by adjusting that potentiometer screw, you're not going to be adding power output to the turbine. Or for your battery bank, it just tells your turbine when to shut down. Okay, so keep that in mind, that you do not want to mess with that potentiometer screw unless you really know what you're doing, and you're doing it for a reason. So only reason why you turn up that potentiometer screw would be if you have a resistive load in the system and you have a diversion capable charge controller, or if you have a specific sealed battery that likes to see a little higher or a little lower voltage cutoff point, and then in that case you might want to adjust that potentiometer. Also, if you're seeing erratic behavior with the turbine potentially shutting down, one of the things in tech support we might say is if the potentiometer somehow got that screw got misadjusted. So keep that in mind. So we were talking about the three things we recommend: ammeter, stop switch, and breaker. And this is a little wind control panel that we sell that combines all three of those things into a nice little easy wiring package. This is very good for customers who are going to be doing their own installs, or for dealers who want to dealers and distributors who want to make it easy for them in the field. You can see it's wind in, battery in, very simple. And you have your this is a higher quality DIN rail breaker, and you got your stop switch and just an analog ammeter. Very simple but very effective, and we sell a lot of these because it just makes it easy for the install. A few tech specs on the turbine itself. All of our turbines have a 5-year warranty. They all mount on that 1.5 ID 1.9 OD pipe. Um, the survival wind speed is 110 miles per hour, but that doesn't mean the turbine won't have issues if you let it run wide open in 110 mile an hour wind. If you know you're going to get those kind of winds, I would hit that stop switch or tie back the blade set or take the blade set off, that sort of thing. So keep that in mind. It's just not going to blow up and be torn apart at 110 miles per hour based on a good installation. So keep that in mind. Here's your cut-in speeds, 7 to 8 miles per hour depending on the turbine. And frankly, there's just not a lot of power in the wind at these cut-in speeds, so keep that in mind. The turbine is small. It weighs 13 pounds, 1.2 46-inch, 1.2 meter 46-inch rotor diameter, about a 1 meter swept area. So it's a micro turbine. It's used for small battery charging applications, for trickle charging, that sort of thing. In wind, we talk a lot about tower height, but when you have a micro turbine such as ours, you don't want to really spend that much money on your tower because you have a $850 retail price on a turbine. Does it make sense to spend $1,000 or $1,500 or more on a tower? So kind of the sweet spot for our turbine is between 30 and 45 feet. Often we see people installing it even lower than that. Oil and gas will install, in oil and gas industrial in North Dakota, Texas, and so on, will install at 15 feet. Just because they have screaming winter wind speeds and they don't need a lot of tower height. So, but as you can see from this diagram, the higher up you go, the more energy production you're going to get out of your wind turbine. So always keep that in mind for when you're talking about towers. The higher the tower, the better, but does it make sense from a financial standpoint to invest that kind of money in the tower? What's more important is really siting the turbine. So the most important thing in siting a wind turbine is you want to put your turbine on the prevailing wind side of any object that's going to cause turbulence, such as trees, house, etc. So this is a good example of that. Here you can see this is the best placement for the turbine if the prevailing wind is coming from here. If you put it behind this house, you got turbulence coming off of those objects, so you have to get it high enough above to get in that good laminar flow wind, which sometimes you can't do with a small wind turbine. It costs too much. So keep that in mind. Water is really great. Anything on the water, around the water is great because you have zero surface roughness, zero turbulence really on the water. On a hill, you have, as the wind flows up the hill, it begins to compress and you have increased velocity. So that's always a good thing if you have a hill. Cliffs and mesas and plateaus and so on, remember, create a lot of turbulence, as well as a building, remember, for building mount turbines. So anytime you have this kind of a situation, you're going to have a lot of turbulence, and that's going to really affect your power output of the turbine. That's why generally we don't recommend a building mount, and we never recommend a building mount if it's an inhabited building. Now we do have a number of customers who use our roof mount kit on a energy shed or a small barn, any uninhabited buildings, because it makes the install very simple and easy and inexpensive. So that can be done, and we've seen it done a lot, but just keep in mind that it will reduce your power output. You won't achieve the power curve on that wind turbine if you do mount it on a building because of all the vertical turbulence coming off the building, as you can see here in this picture using this plateau mesa situation. So the hybrid system is really the key to what we're doing now, and really the key to off-grid in the future. Multiple charging sources, renewable energy charging sources make sense. Most people for many years in off-grid had a generator as a backup, but now with the cost of solar and wind coming down and being relatively inexpensive, it's a much better idea to have multiple renewable energy charging sources in an off-grid system. So solar is wonderful. I have solar in my house, and Flagstaff, Arizona. It works great, except for it does have low output during the winter months due to the shortened days. It has diminished output during bad weather, and no output at night. So wind power is great because the average wind speed it tends to be higher in North America, obviously, and other places in the winter months. The air density is higher during the winter months. And if you can see here, this wind power equation, right here. Let's get a little bit nerdy here for a second. And I can tell you that the three items that are important in the wind power equation to produce power are air density, velocity, which is cubed, and swept area. So air density is a smaller aspect to the wind power equation, but still important. And we know that the colder the temperature are, the more dense the air is. So the most important, obviously, is wind velocity. There it's cubed, so how much your wind speed is, and then swept area. As we say, wing in the wind, right? So the bigger the blade set, the bigger the rotor diameter of the blade set, the more potential power output you're going to get from that turbine. So wind is on average stronger during these bad weather conditions. The old saying, when there's weather, there's wind, that actually does hold true. And I'm going to show you some data to prove that. And wind frequently does blow on those long winter nights and at night when you often need that power. So when you're getting no power out of the solar panels. So these are 4 tenets of why it's important to incorporate a secondary charging source like a wind turbine into your off-grid renewable energy system. So here it is, right? Hybrid systems are complementary. It's like Mother Nature telling us if we live off-grid, we should combine wind and solar together. And in the summer, the solar is doing all the heavy lifting, charging up those batteries, working great. And in the summer, the wind turbine isn't doing a whole lot. It's kind of a lawn ornament, right? It's kind of an ornament there, waiting for storm periods, winter months, when it's needed to help out that battery system. But then you got the winter months, November, December, January, February, March, where you have lots of storms, you have shorter days, and that's when your wind turbine is really helping you to keep that battery from being discharged greatly. And so that's this complementary curve, this complementary nature, opposite curves, right, of wind and solar. Here's a wind resource map for the winter months. And at Primus, with hybrid systems, all we do is focus on what is your winter wind speed. We don't look at average wind speed. We just look at winter wind speeds. And so the darker the blue color, the higher the wind speed. So you can see the coastline, right, has pretty good wind around the Great Lakes here. The middle portion of our country has lots of good wind. This is why all the industrial scale wind turbines are typically located here. We have these mountain zones. That's why you have these islands of wind here, Cascades, the Rockies, and so on. And so lots of good places have good winter wind speeds. So when you're trying to determine whether you want to install a wind turbine at your site, the first question you really need to ask yourself is, what is my wind resource? Because our recommendation at Primus Wind Power is if you don't have at least 4 meters per second or greater of wind, winter wind, then you're not a good candidate for a wind turbine or a hybrid system specifically. If you are lower than that, then you either need to rethink why it is you want to put this turbine at your site, or you need to add more solar and more batteries. But if you do have, and many sites do have a good 4 meters per second or greater wind speed, that's about 10 miles per hour or so of winter wind, then you're a good candidate. So how do you do that? Well, you can go to our site under What's My Wind Resource. It's on the front page or the home page of our site, or you can email me or our customer service line, info@primuswindpower.com, and we can provide you with a wind resource assessment of your site. This data is very good. It's 200 meter resolution data, as low as 10 meters in tower height. So we can take that tower that your turbine is going to be on down to 10 meters, and the spot is somewhere within a 200-meter radius of where you told us that site is. And we need an address or decimal data coordinates to really be specific to find out what your wind resource is at your site. You can't just tell me, your city, Alamogordo, New Mexico. You have to give us a more specific information on your site because, there's a great diversity in wind resource from one side of town to the next. I know here in Flagstaff, the east side has great wind and the west side has very little wind. So, so that's something to keep in mind. So we do have resource information for all over the world, New Zealand and Australia and so on. Almost any place that you give us a coordinates for, decimal data coordinates preferably, we can find a resource for, unless it's super remote. So we talked about wintertime factors, and we know that as it gets colder, this increases wind turbine energy production, and that's just what this slide is saying. And you can get additional 5 to 15% summer versus winter power out of your wind turbine just by the air density. So that helps during the winter months. So the colder the temperature is, the better the wind turbine likes it. This is some slides in Texas, Wyoming, and South Dakota to represent this idea of when there's weather, there's wind. And so you can see over here you have solar energy on this axis, and the vertical axis you have the wind energy, solar energy increasing on the horizontal axis, and wind energy increasing here. So you can see the curve going up. And that basically is saying as your solar energy decreases, your wind energy increases. So this is all plotted data using NREL's 30 years of data from the NREL 240 NREL sites across the country. And so basically the conclusion is when it's less sunny, it tends to be more windy on average when you have bad weather. Now that's obviously not going to apply every day when it's cloudy, but generally it makes sense, right? As the storm is moving in or storm is moving out, you have those clouds, you're going to have that movement of air, and you're going to have more wind. So that helps, right? When you know that the solar panels aren't doing as well. So here are some actual curves, again using NREL data. The most pronounced here is Billings, Montana, and the red is the wind and the blue is the solar. And you can see here in the winter months that the wind turbine and the wind is doing really well and the solar is not. And so again, the complementary curve, the complementary nature of solar and wind is illustrated in these three graphs. I think if you've been in wind or worked with solar and wind for any period of time, or if you just listened in your high school science classes, you know that there's a big difference between the solar day between June and December, right? And this chart just illustrates that you're not going to get a lot of power out of your solar panels in December because you have a limited day, and it's quite pronounced in many places. You can see here by this graph there's a fairly significant difference in daylight hours between June and December here in Rapid City, South Dakota. Again, using NREL data from 1961 to 1990. So that's why with off-grid systems, everybody designs their system for the middle of December, right? And you have, fairly large PV array, fairly large battery bank, 2, 3, 4, 7 days of autonomy on your battery bank. All those things are designed in your system so you have so you can survive those winter months without dropping your battery level below that magic 50% maximum depth of discharge, assuming you have standard lead acid batteries, which most customers do, most off-grid customers do. So with a hybrid system with wind in the mix, that paradigm changes, and So you then potentially can downsize your PV array, you can downsize your racking, you can downsize your battery bank, solar charge controller, all kinds of things that then those little savings can then add up to the cost of adding a wind turbine or two into your mix of renewable energy charging systems. So that's what we're kind of getting at here. Is it makes a lot of sense, as well as getting that nighttime power production in there when you have no power production out of the solar panels. This is a Trojan brochure, right? So it's all about depth of discharge, right? What we're doing with your solar panels, your charge controller, with your wind turbine, is we're trying to keep those batteries happy. And they're happiest when they're above that magic 50% depth of discharge. If you can keep those batteries within this 30 to 40% max range, you can see how steep this curve is up the number of cycle life. So if you get out of this 50% more into the 40 and 30%, you increase the cycle life, the number of cycles of your battery bank. Therefore, you save money, 12 to 18 months, 24 months, whatever it is, longer on that life of your battery bank, can really help you quite a bit. And as we all know, if we've been in off-grid for any period of time, it's kind of a pain to change out a battery bank, right? They're heavy, they ruin your jeans. So battery life will be extended by adding a wind turbine in if you are in a good wind resource. Again, 4 meters per second or greater. So that's really, the crux of the argument. So a little bit about the Air product line. Been around a long time, 1995 with the 303, 403 in 1998. Then we came out with the Strathos Swim Power came out with the X, and then the Air 30 in 2011. Then the Air Breeze and Air 40, and then now the Air Silent X. So lots of wind turbines, over 160,000 now on the market, and by far the largest selling micro wind turbine in the world. And what this means is, we've had lots of time to improve the turbine. Lots of dealers out there, lots of distributors, lots of authorized service distributors, people who work on the turbine have parts. They're all over the world. We have 11 ASDs all over the world. So it really makes for a user-friendly turbine where wherever you go, you can get parts and pieces for the turbine, as opposed to another turbine that you may have a very difficult time getting parts and pieces for, and tech support is all US. So lots of benefits to the fact that we've been around for a long time, and there's lots of turbines out there. Here's the blade sets. The Air 40 is a wider blade, quieter blade, versus the Air 30. It's narrower, spins at a higher RPM, 1,800 RPMs versus about 1,000, 1,100 for the Breeze 40 blade. So this blade, the Air Breeze Air 40 blade, is better in those low to moderate wind speed environments, better on shorter towers, better in terms of sound output. It is much quieter, 65 decibels and under, whereas this Air 30 blade can be over 100 decibels at higher wind speeds. So, and then of course you have the blue blade set I showed you earlier, which is the quietest of all of our blades. Here's a power output. Now, power output is instantaneous power in watts, right? So this is just telling you at any given point when the turbine is working and spinning, this is what you can get in watts at a certain RPM and a certain wind speed, right? So here's your power curve here. The red is the 40, Air Breeze, Air 40. The blue is the Air 30 Air X Marine, right? And again, here we go. There's your blade set for the Air 30 Air X Marine. Here's your blade set for the Air 40, right? And so you can see this is a power curve, an actual power curve, right? This is not made up data. You can see that in the lower wind speeds that you get more energy production out of the Air 40, Air Breeze, and the lower wind speeds. Where it starts to have superior performance is at the higher wind speeds, when you're getting 24, 25 miles per hour and above, up to 30, 35. That's when you get, the high, up to over 400 watts out of the turbine because of those high wind speeds, and it's spinning at a higher RPM, right? 1800 RPMs. Again, it's louder though. It's quite a bit louder at these high wind speeds. So it really, we really want to make sure the turbine, you get the right turbine for the right wind speed and the right environment. In a lot of cases, people don't want an Air 30 and Air X Marine because they just don't want the sound. It's too loud. So in those cases, we would recommend the Air 40, the Air Breeze. If you're in an industrial environment or sound does not matter to you, you like the sound of your wind turbine, which some people do. If you're in a high wind speed environment, the Air 30, the Air X Marine is a good choice. So it really depends on what your wind resource is and what your preference is. Really, more accurately, you should be looking at the monthly energy output curve, which is power over time, right? And that's in kilowatt hours and monthly wind speed. And so again, here the Air 40, the Air Breeze outperforms the Air 30 unless you start to get these lines begin to converge at higher wind speeds. So if your average wind speed is 13, 14, 15 miles per hour, monthly average wind speed, then, and you're okay with the sound output, you could go with the Air 30, the Air X Marine. Remember, keep in mind, any turbine we can put that blue blade set on to quiet down the turbine. Now, I would not recommend that blue blade set in a very high wind speed because the blade set itself has a very steep angle of attack on it. So that's something to keep in mind when you're deciding if you want to go with that blue blade set or not. Now I'm going to go ahead and turn on my webcam here for a second and show you the blue blade set. And you should be able to see me, and here's the blade set, and you can see it does have it's hard to see, I'm sorry about that, but it does have a fairly steep angle of attack on the blade. And so because of that, it's aggressive in those low to moderate wind speeds. So it's going to start spinning up fairly quickly, and whereas the black blades are a lot less steep of an angle of attack. So that's why typically I would not recommend that you, in a very high wind speed environment, that you go with this blue blade set, because it'll spin up so fast, the control algorithm in the turbine will then say, hey, shut down, because it'll be pushing well above that wind speed. So keep that in mind. These will often, if you have a very high wind speed, it likely would go into overspeed protection a little bit faster. So keep that in mind. I'm going to go ahead and turn off my webcam now, and I think I made that point. I hope I did. And you're always welcome to give me a call and we can talk about it more. Here is the sound output data for the Air Breeze Air 40. You can see it doesn't exceed 65 decibels. The green is the background noise and the blue is the turbine operating. And you can see the green and the blue all here clumped together. And then, relatively low sound output. And then you start to see the blue isolating itself. And that's when you start to hear the turbine a little whistling. The Air Breeze, the Air 40 will whistle a little bit in those high wind speeds above 25 miles per hour or so. And that will be that 65 decibels. The Air 30 and the Air X Marine is much louder. So it's significantly louder than 100 decibels in very high wind speeds. So keep that in mind. And the blue blades, we're working on the data on the blue blades for sound output, but we have anecdotally confirmed that they're typically below about 40 decibels max. So they're very quiet. So let's look at some pictures, and then we'll take some questions at the end if anybody has any questions. So here's a wind turbine in a small cabin on a 45-foot guide tower. Um, very common installation for us. Another remote application here on the Himalayan steppes, a very short tower. You can see zero surface roughness here. So a great place for wind, as you can imagine. Lots of turbines on sailboats across the world, thousands of turbines on sailboats. This is an air breeze on this boat. This is a 11-foot mast and stay kit. Here is a turbine, a Air Silent X on the back of this stern of this boat in Oregon, solar and wind combined together. Breeze on a boat in the Caribbean here. Here's your turbine here on the mast of this boat. A little better installation point than on the stern, right? Get you up out of all that rigging and so on, but you're still going to get some turbulence off the forward mast and so on. But remember, you always got to be able to get up to that turbine, so to do maintenance. So keep that in mind. Here is a turbine on the radar arch on the back of this trimaran, and here on the mizzen mast. Two turbines and solar panels on this boat, cruising across from the Intercoastal Waterway to the Bahamas. Here we are, San Carlos, Mexico, and here are two turbines. And those are the old white blade sets from Southwest Wind Power. They sold those for about, I don't know, 8 or 9 months back in the 2008, I believe, and realized that they had a serious issue with they were defective, and so they took them off the market. So haven't been sold in a long time. Here is a parking lot light configuration in Colorado with turbine and solar panel and parking lot light. We do quite a few of these, not necessarily this design, but quite a few of these. This is oil and gas installations in Colorado, North Dakota, South Texas. You can see very short towers, but because of the zero surface roughness and the fact that these are just augmenting the solar panel, they don't need a very high tower. This is a skid, a power skid, 500 watts of solar. You got your 800 amp hours of batteries in here, your solar charge controllers and so on. And then this is what's called a self-supporting lattice tower with a stub pole that slides up through it. And then you have your Air 40 wind turbine on top of that. This is a buoy platform on a tailings pod at a mining operation. These are remote trailer applications for remote airports to scare away the birds and so on. And this is a raptor, plastic raptor, scaring away any migrating birds there. This is Antarctica, the bottom of the world. Multiple turbines on this science site here. One thing I want to point out here is you have the turbine at different elevations so that there's no downwind shadowing effect between the upwind turbine and the downwind turbine. If these were at the same elevations, you'd have that downwind effect, so you got to put them above or below the forward turbine. So keep that in mind when you're doing a multiple turbine installation. Same thing here, two different elevations, solar and wind on this buoy platform. Here is a telecom application in a developing country. Here is this is for positive train control all throughout the U.S. and Europe. They're using our turbines for remote applications on the tracks. This is an RV application next to this Palapa. This is the Sea of Cortez. And then this is Alaska, a very remote location in Alaska. You can see that the solar panel is not doing so well, but this wind turbine is spinning like crazy. So there you have it. There's my information, and I sure appreciate your attention and interest on this call today. I hope you learned something, and feel free to reach out to me if you have further questions or any needs that you might have. And right now I'm going to open it up to take questions if there are any questions. All right. Well, thank you very much again for your attention, and feel free to reach out. Have a great day.